Another question I want to ask you, okay, is what is the electric field? We still have one place in space that we don't know what is the electric field, right? We know what's going on here. We know what's going on inside the wall, but we don't know what's going on in the center, in the place with the air, right? So I want you to be really careful about it, okay? So what we're going to do, so right now I'm looking for what is the electric field? What is the electric field of R that are actually smaller than A, right? This is what's going on in the air in the middle. So we can do the same thing again here, but what is the charge inside? The charge inside is 0, okay, that's what we are looking at. So we need to solve this thing again, right? E, many r's, dA cosine alpha, right? This is actually the flux. And we know that Q inside is actually 0. And I want you to be super careful. It doesn't mean, and lecturer love to put this in exams, okay? It doesn't mean that the electric field is 0. It means that the flux immediately 0. That's what it means that the charge is 0. If you want to say that the electric field is 0, you need to somehow take E outside of the integral, succeeding doing that. In our case, it's going to be easy, right? Because we're going to split again, it's to the leads and to the envelopes, right? And we know that this one is cancelled, and we left with this, which is E R multiplied by 2 pi R multiplied by H, right? Equal to 0, okay? We are okay. This can cancel out, and we actually have that R inside smaller than A equal to 0, okay? Got it? Last question, and all the idea of the next question is to show you that this concept that saying the electric field is 0 is wrong, is this one. Imagine that we have some bubble, okay? We have some bubble and it's charged, okay? It's a really short question. A bubble, and the bubble is charged, bubble in the water with some electric field in the shell, okay? Here it is. So some constant electric field in the shell. But we also have in space, by the way, what is the electric field inside a bubble? We can do Gauss's law, right? Of also a bubble, right? This is E bubble, cosinus alpha. If you're going to draw a small spherical, right, here, we know that the electric field is always pointing at that direction from symmetry, right? It's always going to point inside. So cosinus A is actually 180 degrees, which means it's -1. E, only a function of the radius, right? Because of the symmetry. So this is a function of R, of our sphere size. R can go outside of the integral. E bubble R equal minus, because of this sign, the size of the spherical, which I recommend you to learn it by heart, 4 pi R square, equal to what? To the charge inside it, Q in A, right? And in our case, all the charge is on the outside, so this is 0, right? This cancel out. E bubble, I know, must be 0, okay? But if I'm going to put here a point charge, Q, what is the electric field of this thing? It's going to produce electric field all over the place, right? K R square, K Q divided by R square. You see it? So right now, you cannot use Gauss's law for the symmetry, right? You don't know how the electric field behave here, right? Look, this dA, and look at this electric field, right? This Look at this electric field and this dA. This dA and this electric field. This dA and this electric field. Like there's many. You see how complicated is it? So how we can solve this kind of problems?
Gauss and no superposition.
Open the box. The solution is inside. Cameraman, please. So, why? What attention? What is it? Okay, so in order to solve, sometimes the problem would not be symmetric like we had right now. But I know you can only, yeah, exactly. Sometimes the problem would not be as symmetrical as we had here, right? But we know that according to the superposition principle, right? We know that it's actually equal to what's in the wall. We have the bubble, and we have also the contribution of the charge, superposition. Who are all the players in the game? And we know that this one, if it was alone in space, it was B0, because then the wall was be asymmetric. So we know that the electric field inside is only this one by this effect, okay? So what I want you to take from this, and this is the last thing, is if you have in your problem something that is not perfectly from Gauss's law, you cannot use Gauss's law, you don't understand what is the electric field, ask yourself, can I split with superposition the problem and then solve part of it with Gauss? And then the other one understand by Coulomb's law? And then you can solve, okay? That's it, guys. Next week, we're going to talk about potential and about energy, okay? So see ya next time. Thank you.